Okay. So today I will talk about linear regression, which includes ordinary least squares and penalized least squares. So let's first look at the ordinary linear regression. So say I have the linear model. So this means I have n data points, y1 to and X is my data matrix or feature matrix or design matrix. It has n rows and p columns. So each one is 1, 2, and this is data. This is the regression model which I don't know. P column. Epsilon is in by one noise. That takes epsilon 1 to 7. And I'm assuming each of the noise terms are I,1000. And for now, I assume we will stand on our standard Gaussian. So we know y and x, and our goal is to estimate beta hat so that the two norms of beta hat minus beta is minimized. So this is the most classical setting of linear regression. So one obvious way to do this is least squares. Or in this simplest case, it's called ordinary least squares. Let's solving this optimization problem. So I'm finding one linear model beta such that the x beta best fits the response variable. So in class, this is equivalently written as logarithm. So these two things are equivalent. This one doesn't really matter because it's a multiplicative factor. So that can be shown. So let's first see how do we get a closed form solution for beta hat. And like this is all in class. So the best way is to compute the gradient of this guy. So let's say f is I want to compute the gradient of beta with respect to beta. That is you can check this by reading matrix book. Like this is basically the same with scalar version, where you have a squared function, you take the derivative is 2 times 1 minus beta, and you get x. So I will say this being 0. And I will organize the terms. I will get x transpose x beta Now, assuming x transpose x is invertible, I have beta. So what exactly is the condition that x transpose x is invertible? So consider the singular variable condition. How many of you know singular variable condition? Most of them? Most of them? Okay. X is u sigma v transpose. So x is n by p. So this u is n by n. This sigma is n by p. This v is e by p. Like both u and v are orthogonal matrices, and the sigma would be something like it's a rectangle. Sigma n by p, like the sigma lines. So the condition that x transpose x is invertible is equivalent to sigma p larger than 0. So x has p non-zero singular values. And under this assumption, beta hat can be expressed in this very succinct way. Okay, so some more remarks on this OLS estimate. So first, if epsilon I are IID Gaussian, then beta hat is maximum likelihood estimation. Why? It's very simple. You can see P of y given x beta, yi given x beta is 1 over 2, 1 over 2 pi. Right? Because I know y beta would be epsilon. So you can see, in order to maximize the likelihood, you maximize the sum of the log likelihood, so you minimize this part, summing over I from 1 to n. Right? So beta hat maximizing this this is equivalent to beta hat minimizing so this gives you OLS. This formulation is ordinary least squares. Okay, so ordinary least squares is maximum likelihood estimation when epsilon I are IID Gaussian. Can I erase this? what is the y hat? The predicted value of the predicted value of this is my prediction of the expectation. So y hat would be theta hat, which will be x. So this is the projection of y onto the subspace spanned by the columns of x. So this is a low-dimensional subspace because I have n, so each vector is n-dimensional, but I only have p of them. So it's a rank p subspace. I'm projecting the n-dimensional vector y onto the rank p subspace. And this gives me the estimate of the ordinary space. Third property, that OLS is unbiased. What does this mean? This means the expectation of theta hat, where the expectation is taken over your noise variable. The expectation is exactly the same with the original model data. Any questions? So how do you prove this? It's very simple. So expectation of theta hat would be the expectation of x transpose x inverse x transpose y. It would then be the expectation of x transpose x inverse x transpose x beta plus epsilon. Right? This, so x transpose x inverse, x transpose x, they cancel out. So I have beta here, and I have the expectation of x transpose x inverse x transpose epsilon. And the x are fixed, they are not random. So this will be theta plus x transpose x inverse x transpose expectation of epsilon. And epsilon are noise terms, so they have zero meaning. So this would be theta. So this means the ordinary least squared estimate is unbiased, in the sense that the expectation of the estimate of theta hat would be exactly the same with the underlying true data. So you can imagine if you perform this a lot of times, you will get something that is concentrated on one data. And similarly, you can prove that in this OL assessment, the expectation of y hat will be exactly the same as x beta. Because it's x transpose x inverse, x transpose x beta. You cancel the x transpose x out, you have x beta. And the noise term epsilon is again has zero meaning. So the expectation of the estimated y would be x beta. Similarly, we can, okay, I will not prove this, but I will just tell you we can also have like a variance of theta hat. This would be this would be x transpose x. So imagine your data point x are for example, are samples from a Gaussian distribution 0 with covariance sigma, then this X transpose I will go to n times sigma, and therefore the variance of beta hat will be 1 over n. So X transpose is inverse. So in this case, X transpose X will go to n sigma, and the variance will be 1 over n sigma inverse. So assuming this sigma does not change, your variance of your estimate goes down as 1 over n. So if you have more data, your variance will go down as 1 over n. And combining this fact with the fact that beta hat is unbiased, you get the mean square error. The mean square error will get minus beta to go down as 1 over n. So as I see more and more data, I will the error of estimating the true beta will go down very quickly to 0, and this scale is 1. Okay, now I'll talk about penalized least squares. The easiest example of this class of estimator is if I have lambda, I'm still trying to minimize the error of fitting y using x beta. But this time, I'm adding a penalized term to the objective. So why do I add this penalized term? I can think of two reasons, at least two reasons to add this term. First reason is that I believe beta should be close to the, beta should not be too large. This actually makes a lot of sense because, for example, if you have something like beta p equals 10 to the 10, you might really like doubt whether your model is correct or not, because in most cases, your regression model cannot be that the value of your regression model cannot be that large. Another reason is that by adding this this L2 penalty term, I can guarantee that no matter whether X transpose X is invertible or not, the optimal solution always exists and is unique. So if lambda is larger than 0, I always have data that has lambda equals X transpose X plus lambda I. So you can see this matrix is always invertible as long as lambda is larger than 0. That doesn't really matter whether X is X transpose X is invertible or not. It's always invertible, and therefore I can always guarantee that there is a unique minimizer of this objective. So that's another reason why this penalty term matters. So now I will analyze some properties of this estimator. So let's first see what is this one. You can see I again plot y equals x theta plus epsilon theta for y. And I'm also using the fact that the expectation of epsilon would be 0. So in this case, I get lambda I. So you can see this estimate is no longer biased because this is not equal to beta, where lambda is not 0. If this is lambda is 0, I get x transpose x equals x transpose x. This equals to beta. But now I have a small bias to lambda I, so it does not readily equal to beta. And in order to see what this exactly is, I'm again using singular value decomposition. So let's say x is in sigma v transpose, and to write it out, I'm saying x equals sigma p, sigma and sigma 1, sigma 2, sigma p. So using this singular value decomposition, we can see precisely what this rich regression is doing. Okay, let's now use x equals to sigma v transpose to rewrite this equation. So this is because U is orthogonal, U transpose U will be identity. This U transpose U will also be identity. So I have so the next step is to use the fact that V is also orthogonal. So you can write identity as so V transpose V equals V transpose identity. So with this thing is V plus V transpose inversion V transpose beta. And because V inverse is V transpose, because V is orthogonal, this term becomes again, V transpose V equals identity. So what I get is V okay. So what does this really mean? So here, a very first observation. What if lambda equals 0? What would I have for this entire stuff? If lambda equals 0, this thing would be sigma to the minus 2. It cancels out with sigma squared. So this thing will become V transpose, which becomes identity. So this means for the unpenalized case, I get identity times beta. So in other words, the limit of lambda goes to 0 expectation of beta lambda at p beta. Because when lambda goes to 0, I reproduce the ordinary least squares estimated, and I will get this thing. So I will again get the unbiasedness. So when lambda is not 0, what do I get here? So let's actually write to the P. Again, it's VI transpose. But this time, I have another term in front of this. The term is sigma I squared divided by mass I squared plus lambda. And I'm multiplying this with beta. So this is like okay, divided. So see what this means. Okay, projection of the true model beta. Let's see, this is the true model beta. This is a projection of beta onto like an orthogonal space, autonomous space Vi. So this is Vi. This would be the projection of beta onto Vi. And then I'm reproducing this Vi. So without this term, I'm just projecting beta onto all the P basis vectors of an orthonormal basis. Then I'm reproducing it. It will be exactly the same with beta itself. But for the ridge regression case, every projection is shrinked here. It's shrinked by a factor of sigma squared divided by sigma squared by plus lambda. Note that this is always larger than, smaller than 1, if lambda is larger than 1. So you always shrink the projection. So that's somewhat like I'm projecting beta onto all my Vi's, and then I shrink each vector. After that, I reproduce this Vi. So as a consequence, the entire beta will be shrinked because I'm shrinking on every direction of my basis. And the amount of shrinkage actually depends on the singular values, so sigma I. So this means if the singular value is really large, I shrink only a little bit, because if the sigma, if the, for example, on the principal direction of S, sigma 1 will be very large. This means I have a sufficient amount of information here. So I don't really need to shrink it a lot, because I already have a lot of information here. I can trust my estimate, so I only shrink a little bit. However, on the least single value direction, sigma p, I only have a tiny fraction of information. So I'm not very confident of my estimate on this data set, because this sigma p is so small. It's really a very little information. So on this direction, I'm shrinking the final estimate a lot, because when sigma I is small, this lambda will be dominating. So I'm shrinking it a lot, so that the final reconstruction will not ruin the entire beta vector, because it's shrinked a lot. So that's the general intuition behind this L2 penalized least squares. Any questions? Okay, I think I have all I have today, so I can answer questions. If you have questions on either the lectures or the homework or the program. Yes?
So it says that the prediction needs to be deterministic. We tried a lot, but fixing the randomcy doesn't actually determine it. It does
Which one?
So we're using a random forest classifier. Giving it a fixed seed doesn't actually determine it. So is it okay if it's close by? Like the scores are really close.
I see.
Gives it
So
consistent.
in general, if it's quite stable, you don't worry about it.
Okay.
Yeah. Or I'm actually curious why it doesn't determine as well.
Yeah.
Which language are you using?
Python. So we need to see the
Maybe there's some
other generator that's not seeded.
Yeah, in that package. Maybe there's a seed for the package. I don't know.
Yeah. Okay.
Yeah, that's probably. But if you can get stable results, you don't worry about it.
Okay.